So today we're going to cover Chapter 10, Section 6. We're going to talk about segment relationships and circles. So the first one is a definition, and it's defining segments of chords. So when two chords intersect in the interior of a circle, each chord is divided into two segments called segments of the chord. So in this particular picture, we have chord AB here. And chord AB, once it intersects the other chord, it's breaking it into two little pieces. So from A to E, this is a little segment. And then from E to B is another segment. Then I also have segment chord CD here. And it also gets broken up into two little pieces. So we've got four little segments when two chords intersect. Next, we're going to talk about finding the lengths of these segments, or just maybe even also finding X. So again, don't memorize the number. You can memorize the name. It's called Segments of Chords Theorem. And this one states if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So for example, again, it's breaking it apart into two little pieces. So again, you have chord AB here, and again, it's broken up into this little piece and this little piece. And then you also have chord CD here, which is also broken up into two little segments. We have this segment and this. So let me add some numbers into this because the chords here are not congruent, but their products are. So for example, and again, this picture is not drawn to scale. So let's say AE is 4, and let's say I give EB 6, and then let's say DE is 2, and then CE is 12. So if you plug it in, and if you see EA, I said is 4, and EB I said was 6, and then if I set that equal to DE or EC 12 times 2, notice their products are equal because 6 times 4 is 24, and 12 times 2 is 24. Their products are equal. But if I were to go back and add the length of AB, 4 plus 6 is 10, and then CD, 12 plus 2 is 14. So notice the lengths of the chords are not congruent, but their products are. The next definition is a secant segment, and a secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. The part of a secant segment that is outside the circle is called the external segment. So in this picture, right now we're just talking about the red. So the red here, this entire thing is the secant segment. But the darker red, the piece of that secant segment that is outside of the circle is called the external segment. So this piece right here of the whole secant segment. Now, on the next slide, we're going to define a tangent segment. But notice that for the secant segment, it's passing into the circle and it's touching the circle at 2 points. What we're going to see with the tangent segment, it's only going to touch the circle at 1 point. And we're going to see that definition on the next slide. The next one is the tangent segment. And a tangent segment is a segment that is tangent to a circle at an endpoint. So again, it's touching the circle at only 1 point. And the tangent segment in this picture is the blue. The formulas define the angles whenever we had two tangents, two secants, or a secant and a tangent, remember the formula for all three of those scenarios was the same. It was big arc minus little arc, divide by 2, and it gave you the outside angle. Now, they're different formulas for the segments. So let's go ahead and take a look at the first one. The first one is when we have two secant segments. So this segment's of a secant theorem, and this one states, if two secant segments share the same endpoint outside a circle, then the product of the lengths of the one secant segment and its external segment equals the product of the lengths of the other secant segment and its internal segment. So bottom line, we're doing the whole length. So ln, this whole length of this secant, times its little external piece. So we're doing whole times external, and then we do the same thing here. The whole thing times its little external piece. Remember, we've already saw at the beginning when there's two tangents, those two tangents are congruent. So the only new ones we're doing here are this one, when there's two secant segments, and then the next one when there's one secant and one tangent. So the next one is the segments of secants and tangents theorem. So in this picture, we have one tangent segment and we have one secant segment. So this one states that if a secant segment and a tangent segment share an endpoint outside the circle, then the product of the length of the secant segment and its external segment equals the square of the length of the tangent segment. So over here is my tangent segment. So I'm going to square that and set that equal to the secant segment, so the whole thing, times its external, which will be this little piece. And this is for the secant segment. So it's going to be tangent squared is equal to whole times external. And now we're just going to do examples of these theorems. So for the first example, we've got two chords that are intersecting inside the circle. Now that is an X. It sort of looks like a plus sign, but it's actually an X. I'm going to add in some variables just so we can find the lengths of these chords when we're all done. Notice the instructions only say to find X, but let me add some variables. So I'm going to call this chord right here AB, and I'll call this one CD. So when two chords intersect inside the circle, remember it breaks it apart into little segments. So I have X here as a segment, and then the 3 for CD, and then I have the 12 and the 2. So I'm going to go ahead and set them equal to each other because remember their products are what's congruent, not the chords themselves. So I'm going to do 3 times X for the CD and set that equal to the product of AB, which is going to be 12 times 2. So I'm going to multiply 12 times 2. I get 24. I need to set that equal to the 3x. I'm going to divide by 3, and x equals 8. Now that's all they asked me to find up there in the white writing. However, let me just demonstrate that AB is not congruent to CD, only the products. Because the products, when I multiply them both, they give me 24. So for AB, to find its length, I'm just going to add the 12 plus 2, and the length of AB is 14. But if I do CD, I just found x to be 8, so 8 plus 3, and the length of CD is 11. Again, notice the chords are not congruent, but their products are. So next we're going to notice what we have in the picture. Notice X. Over here, this is a tangent. And then up top here, this is my secant segment. And to find its whole length, I'm going to add 18 plus 6, and I get 24. The external piece is this 6. So the formula to find the value of x is going to be tangent squared is equal to whole times external. I'm going to plug in my numbers. So my length of my tangent is x, so I'm going to square that. My whole, I already did that, it was 24, and the external piece was 6. I need to multiply 24 and 6. I get 144. I'm setting that equal to x squared. Remember, when we're solving for a variable squared, we are going to square root both sides. So I'm going to square root the x and the 144, which leaves me x is equal to plus and minus 12. Now, what we need to do is we need to check to see which one or both are we going to keep. If I were to plug in positive 12, it works because it gives me a positive segment length for the tangent. However, when I plug in a negative 12 up here, it would make that tangent negative. So the only answer, so I'm only keeping out of both of these answers, x equals positive 12, because I can't have a negative length for one of my pieces of my circle or my tangent or my secant. Let's do 2 more examples. Next, we have 2 secant segments now. So again, we're going to use the formula whole times external equals whole times external. So over here, I could say that this is my whole. It's going to be x plus 6. The 6 is the external piece. Then up here, this secant segment, to get the whole, I need to add 8 plus 4. So my whole is 12. And then the external piece is the 4. So I'm going to do 12 times 4 is equal to x plus 6 times 6. I need to distribute 6x plus 36 equals 12 times 4, which is 48. I need to solve for x, so I'm going to subtract 36. 48 minus 36 is 12. Set that equal to 6x. Divide by 6, and x equals 2. So in picture D here, the 10 is a tangent, and then the secant segment, to find the whole, I need to do 2x plus x, and that gives me 3x. And then x is the external piece. So for this one, again, I'm doing tangent squared equals whole times external. So tangent is 10, so 10 squared. Whole is 3x, external is x. 10 squared is 100. 3x times x is 3x squared. Divide by 3. I get 100 over 3 is equal to x squared. I need to square root it. So this gives me, and I could do them individually. I could actually do the square root of 100, the square root of 3, and then I'm gonna, and it's plus minus, so it becomes plus and minus 10 over the square root of 3. Remember, you can never ever leave a radical in the bottom of a fraction. We need to rationalize. So I get 10 over root 3, multiply top and bottom by square root 3. X is equal to plus and minus 10 square root 3 over 3. Now, again, let me go back and look. Is one of these going to make it negative? Yes, it will. So the only one I'm going to keep here again is the positive 10 square root 3 over 3. So on the test, this would be your answer. If you happen to get any questions on an SAT or on Big Ideas, and they say round to the tens place, this is actually equal to 5.77 something, so rounded to the tens place, 5.8. But again, on the test, we're not using a calculator, so you would leave it as 10 square root 3 over 3. We're only keeping the positive answer. Yes. Yes. Let me show one more example where you have to factor it, and then you guys can start your homework. All right, so let's try let me add a slide here. Let me draw a circle. I'm going to actually draw 2 secant segments here. One. So we have, I'm going to put an 8 here, a 4, a 2, and an X. So again, 2 secants. So we're doing whole times external equals whole times external. So for the first one, my whole can be found easily. All I have to do is add 8 plus 4. 12 is the whole, and this 4 is the external. For this one, my whole is 2 plus X. Or X plus 2 if you want. And then the external is the X. So let's plug it in. So for the blue one, it's going to be 12 times 4 is equal to X plus 2 times X. So I'm going to multiply everything. So the blue becomes 48. The purple becomes X squared plus 2X. When you're doing these, try to keep your X squared term positive. So instead of moving the X squared and the 2X, I'm going to move the 48 and set it equal to 0. And now I have a trinomial that needs to be factored. So factors of negative 48 that when I add them give me 2. So this is going to be positive 8 and negative 6. And now I'll put them into the binomials. Set them equal to 0. Subtract 8. X equals negative 8. X equals 6. Now again, you need to check it. Notice when you plug in negative 8 right here, it becomes 2 plus negative 8, which gives you a length of negative 6 for that tangent. And I can't have a negative length. So I'm going to get rid of this one. And the only one I'm going to keep is the X equals positive 6. So again, in the homework tonight, I've given you some factoring problems at the end. They're just trinomials. Tomorrow night's homework has the geometry pictures, the tangent with a secant or the 2 secant segments, where you're going to actually set up an equation that'll be a trinomial that you'll need to factor. When you're doing the big ideas, you need to check your answers. And then you need to plug it back in if it makes the tangent negative or the secant segment a negative segment, then you get rid of that x value. So that is it for 10.6.